Welcome, Mindsetters, to this session of Grade 10 Science. I hope you guys are ready. You've got your pens and pads out, and you're going to make some notes. I've got Phil in here today with me, who's going to be taking us through today's session. So, Phil, what's happening today?
We're going to take a look at some graphs. We're going to be taking a look at graphs of motion, and we're going to be paying a little bit of attention to acceleration today.
All right, awesome. So while Phil makes his way to the board, Phil, I'm going to tell these guys what they need to do. Mindsetters, you know by now that, hey, you need to get on the Facebook page, www.facebook.com/learn extra. Make sure you get on and post those questions. Let me know what you guys are thinking. Because you know the drill. I've got these awesome calculators and this labeler to give away. So make sure that you guys post on the page. Because if you don't post, I can't give these away. And if you also don't post, you can't stand a chance to win these. But on that note, Mindsetters also want to make sure that, guys, if you see a mindset in trouble, make sure that you actually help them out. If the whole point is sharing is caring. And guys, on that note, I also want to send a quick shout out to Liberty. And just want to say, hope you guys enjoy the show. Phil, take it away.
Thank you so much, Ty. Okay, well, as I said, we've been describing motion. We've been talking about velocity. We've been talking about displacement. You guys are probably sick of hearing me talking about vectors. But we're going to be continuing it today, but today we're going to throw in some experiments. We're going to be starting to actually measure motion, which is what I'm excited about. There's an experiment coming up a little bit later on, which you guys might be lucky enough to see inside a classroom. We're going to show you in the studio a little bit later. So what we're going to start doing is we're going to start describing motion. We're going to start putting that motion on some graphs. I'm going to show you how to measure these graphs. Okay. So let's start taking a look at a particular example. And as usual, I got my handy pen. We're going to start taking a look at some of the important information. If you guys are taking some notes, I'd like you to copy down this example and draw these graphs with me, because drawing these graphs, you get kind of a feel of what's going on, and you can make some of your own notes. Okay, so we're going to consider this first example. Now, there's always somebody walking somewhere in one of these examples, and this is no different. So we've got a boy who starts walking at a velocity of 3 meters per second. Okay, so now we've got to highlight what we've got and how much we have of it. Remember, I was telling you right in the beginning, we've got to start paying attention to the quantity and what it is. So we know what it is. We know that there is a velocity of 3 meters per second. Okay, now there's something else on the board which I really want you to pay attention to, and that is the meaning of this unit. Now, some people are kind of like, motion, you got some velocity, you got some displacement, you got acceleration, whatever. They're all the same thing. They're absolutely not. It's all about the units. The units tell you so much about that story. They even tell you the formula and how to calculate it. So, what I've done is we've got this inside some brackets, and I'm pretty sure most of you are starting to read through that already. So it says, in example, it means that he walks 3 meters every second. So when I say 3 meters per second, that means that he's walked 3 meters after each second which has gone by. So he walks these 3 meters in every second. There we go. There's the unit which has actually been broken up. Guys, please, the unit is almost everything in this section. If you know your units, you actually know a lot about what's going on here. Okay, so now how long does he do this for? Well, we're told that he does this for 6 seconds. All right, so each second that goes by, he goes 3 meters. And he's going to do this for 6 seconds. And then he stops. Okay, so there's quite a bit of story going on there. Okay, so let's just go through and revise some of the important pieces of information. We've got this boy who starts walking at a velocity of 3 meters per second. And that means that every second that goes by, he walks another 3 meters forward. Okay, he's going to do that for 6 seconds. So I'm sure that most of you are going, okay, well, he's walking 3 meters every second and he's doing it for 6 seconds. You can start to get an idea that you can put this on a graph and you can figure out how far away he is. If I know that there's 6 seconds and every single second he's going 3 meters, you guys have already started doing the maths inside your head. So I've got 6 seconds, 3 meters in each one of those. We're going to land up 18 meters away. But how does this look if I start to make a displacement-time graph? Okay, well, we'll come back to the second part in a moment. It says that he stands still for 10 seconds, so his position does not change for 10 seconds. That means that he's standing stationary the same way that I am here. Okay, let's take a look at this graph and let's see how we're actually going to do this. So now, let's see how I get my graph, which is over there. Now, I just want to pay attention to this. All of these graphs start to look the same. Now, what I want you to do is when you look at a graph that you've never seen before, take a look at the y-axis, the dependent axis. So what we're going to do is we're going to say, what are we looking at as time goes by? I'm looking at the displacement. That means that we're looking at how far away we are from our starting point. Now what we're going to do is we're going to watch as this goes by in time. Now I want to pay attention to this particular graph. We're going to take this graph into small bits and pieces. Okay, so something has started happening here. I've noticed that after 6 seconds, this boy seems to be 18 meters away. So let's actually plot that out. Let's plot out some of those important bits and pieces of information. There we go. So we're going to start at 6. Let's plot it out there. I know that after 6 seconds, we are 18 meters away. So that's pretty important. Okay, so just remember that that was where we were going to land up. But that's not where I want to pay attention to. What I want to do is I actually want to start taking a look at how we actually drew this graph. So a lot of you are saying, okay, well, he just pulled up that graph from nowhere. Let's actually see how I got there. So let's take away these arrows for the moment. Let's actually start plotting. Okay, so now if you're trying to plot out something like this, make centimeters down the left-hand side, make centimeters up this side, and for every 2 meters, you can make that into 1 centimeter. So now you can actually draw your same graph with us at home. Okay. Now, after 1 second, he has moved 3 meters. So let's actually plot this point together. So if I go 1 second forward in time, what I've got to do is go 3 meters up in displacement. So if I go 1 second forward in time, there it is. What I'm going to have to do is go up to 3. So let's actually plot a point which is exactly over there. What you can see is that that matches up with 3 meters. So that means 1 second forward in time, 3 meters up in displacement. That's the definition of his velocity. Okay, well, let's go forward 1 more second and add 3 more to his displacement. So if I've got 1 second more, let's go up to 6. So what I'm going to find is that that matches up very nicely with 6 meters. So I'm sure that you can actually see that these points which are going up actually correspond very nicely with 3 meters after 1 second, 6 meters after 2 seconds. After 3 seconds, 9 meters. So after 3 seconds, there it is. I've got 9 meters, and that fits in nicely over there. So I'm sure that you can see that this trend continues. I have got a constant velocity. What does that mean? This means that on this graph, that for every second that goes by, I'm increasing my displacement by the same amount. Because remember that velocity is the rate of change of displacement. Now, that sounds a little bit complicated, so what we're going to do is break it down into smaller little bits and pieces. So that means for each second that goes by, I go the same displacement. So from the slope of this graph, in other words, how fast it's going up, I can actually tell my velocity. So my velocity over here was 3 meters per second. So my velocity is equal to how much my displacement changed. So it's my rate of change of displacement. And if you guys have been doing a little bit of maths, rate of change is actually the slope or the m value. So rate of change of displacement. In other words, I can actually find out what my velocity is off this graph. So my rate of change of displacement is the way that I can actually tell how fast something is going using a displacement time graph. Because remember that when I take displacement over time, which is the same formula for m, that gets me velocity. So let me just put up that formula over there. That v is equal to delta x, which is my change in displacement, over the change in time. Now take a look at that. That actually tells me change in y over the change in the x-axis. That's the same as the slope formula in maths. So that's pretty important. That's actually telling me the same thing as my description, is that my velocity is the rate of change of displacement. Okay, so now I know about the first piece of information. I know, for instance, that I've got that 3 meters per second for that first 6 seconds, and that lands me up at a displacement of 18 meters. Okay, now what I've got to do, let's just make some space here. What we're going to do is we're going to take a look at what happened after that 6 seconds. Now, I want you to do this. When you look at a graph, the way to read it is this. I start my sentence with the axis which is on the y-axis, the displacement. From there, we can work further. So let's see what happens to the displacement as time goes by. I can say that the displacement stays the same as time goes by. If I go forward 1 second, I have got exactly the same displacement. That means that the displacement has not changed. So your object is stationary. So that means that my object has not moved. Okay, so now if I was to apply that rule to that first bit of the graph, let's start our sentence this way. As I move forward in time, what am I going to say about my graph? Well, the displacement increases as time goes by 3 meters for every second. Does it stay the same? Well, each second that I go by, absolutely, yes, it does. I can see that displacement is increasing the same amount each time I go forward a second. Now, I'm going to draw on a few triangles, so just to keep track, what I'm going to do is do them in a slightly different color. So let's do that. 1 second forward, 3 meters up. 1 second forward, 3 meters up. If I keep on doing this, I can see that exactly the same increase comes from each second. What we've got here is constant velocity. And I can tell that from the constant gradient for some of you that have already done this. So constant velocity. There we go. So I've got constant velocity on that way up, and on the end, what I've got is, well, let's take a look at that slope. If there's no change, what I can say is that there is no or zero velocity. Okay, so now that was a very basic way of graphing out this boy's position as time went by. We were told that he had a velocity of 3 meters per second, so that is velocity, told us that for every second that went forward, he went 3 meters further forward. And that's what we graphed in the first 6 seconds. After that, he was stationary. So don't panic too much. We are going to be saving these and putting these up online. What we're going to do now is we're going to take a little bit of a change in gear. What we're going to do now is we're going to describe what happens if the boy now takes 9 seconds to walk back to his starting point. So let's highlight that important information. Let's see what goes on. Okay, so now if the boy now takes 9 seconds, so now we know how long it takes to do whatever he's about to do, to walk back to his starting point. So this is quite important. Back to his starting point. That tells me something about the final displacement. I hope that you remember from a couple of series ago that back to his starting point means that his displacement will then become 0. If you land up at exactly the same place as you started, that means that his final displacement will be 0. So that means that his x value is equal to 0 meters. So that's what I've got to plot on the graph 9 seconds later. And then to work out his velocity. So what we're going to do is we're going to take a slightly different approach. We're going to adapt our graph and try and find out what this boy's velocity is when we take a look at the graph. So we've got our original graph, and this is exactly the same as it was before. We've got displacement on the y-axis, and we have time on the x-axis. It's exactly the same. So what we did was we had our 3 meters per second all the way up there. So that meant that for every second that went by, I increased my displacement by 3 meters. For the next part, how many meters per second? Absolutely none. Because what I found was at the beginning of that period and at the end of that period, we found that he hadn't moved anywhere. His displacement was still 18 meters. Okay, well, how long did that last? That was from 6 until, I think we've got until, let's actually take a look at our example. I think it was 9 or 10 seconds. Let's just be sure. Okay, so he's stationary for 10 seconds. That's absolutely right. So let's actually plot that down and let's find out exactly what's going on. Okay, so now I've got 6 seconds. Let's actually divide up our motion. Okay, there we go. So there's our first piece of motion. That's when he's walking at 3 meters per second. Our next piece of motion comes from the part where he stops being stationary. At this point, we can find out that during that period from 6 seconds to 16 seconds, that his displacement did not change. If his displacement did not change, that means that he was stationary. Now note, I've been very specific about the words that I use. Please make sure that you do the same. So I know that during that period, there was 0 meters per second. Every second that went by, there was 0 meters of displacement. Okay, well now here's a little bit of a challenge. I've got a period where I start off at 16 seconds, and this lasts all the way through to 25 seconds. Now, let me just plot what's going on there. So this is 25 over there. So I'm starting at 16 seconds, and I'm ending up at 25 seconds. That means that this period was 9 seconds, exactly as we said. Well, how far did this boy walk in this time? Well, we were told that this boy walked back to his starting position. There it is. 0 displacement. So that means that this boy is now back at his starting position. The starting position means that there is no displacement. Okay, so his starting point or starting position means that there is no displacement whatsoever. So we knew that he had to walk from 18 meters all the way back to his starting point. Okay, well now, how do we figure out his velocity? And what is the difference between velocity and speed? So let's take a look at our graph over here and let's try and decide what to do. Remember I told you that the slope of this graph could tell us important pieces of information? Well, I've got a starting point where at 16 seconds, we find that he's got a displacement of 18. And at the end, he's got a displacement of 0 after another 9 seconds. So what I'm actually going to do is we're going to try and figure out the gradient of this line. So let's do this in a slightly different color so that you can follow. Okay, now the gradient of this line is equal to the change in displacement, which is delta x, over the change in time, which is delta t. Strange enough, that's the same formula that gives me velocity. So change in x over change in time gives me velocity. Now, let's put in some values. These triangles might not be familiar to you, but what they mean is what is the change? A different way of writing this formula is saying x2 minus x1 over t2 minus t1. So that's a way that you might be much more familiar. 0.2 minus 0.1. And that's the way that you've worked out straight lines in maths. So now what we're going to do is I'm actually going to take this down further, and let's see if we can't figure out what the gradient of that line is. So let's have a formula, then we're going to substitute together. So I've got displacement 2 minus displacement 1. Now, just bear in mind that this x is not the same as the x in maths. This x is talking about displacement. Then I've got time 2 minus time 1. So let's find out what the velocity actually is. I know that the average velocity, and that's a word that I'm going to throw around a little bit, is my final displacement, which is 0, minus my initial displacement, which was 18. That's how far away I was. My final time at the bottom was 25 seconds, minus my initial time, which was 16 seconds. Okay, let's just stop there for a second and take in where all these numbers came from. All right, x2 and t2 are the displacement after some time. So this is displacement final, or displacement at the end, time at the end as well. So my displacement at the end was 0. My time at the end was 25 seconds. My displacement initially is 18. That's how far away I was. My my initial time was 16 seconds. So let's simplify this and find out what the velocity of this boy is. Okay, so now I've got 0 minus 18, which gives me a negative number of 18. Whoops, let's make that nice and neat for you folks taking notes. Okay, so there we go. So 18. All right, at the bottom, I've got my 9 seconds. 25 minus 16 gets me 9. Now this gives me a negative answer. So negative 2 meters per second. Now that's quite important. This is the first time we've rocked up on a negative number. What does the negative mean? What we're going to do is, because this is a vector, the sign actually tells us direction. So plus and minus can tell us the direction. So that's quite important to note, especially if you're in grade 10. Plus and minus can actually tell us information about the direction. That means that's opposite to the original direction of motion. Let's think about that for a second. That means that this boy is now walking backwards at 2 meters per second. But that makes sense because he went to one place, he stopped there, and then he came back. So he must have gone in the opposite direction. Now, I can't leave an answer in a negative format when we write out a vector. So what do I do? Let's write this as a positive number and give it a direction like all good vectors should be. So let's do that. If I've got negative 2 meters per second, what we're going to do is now we're going to take that negative 2 and find some meaning out of it. So what I'm going to do is write in my answer here, I will say that my velocity is equal to 2 meters per second back to starting point. See how I'm giving it a direction. So back to starting point. I've given it a direction, I've given it a meaning. I've interpreted. That means that I found out what that negative actually means. So back to starting point. All right. So let's just revise what we did. We saw a graph. Okay, and how did I draw this graph? Well, I started at 18 and I landed up at 0. Why did we know to do that? Well, it tells me in the description that he walks back to his starting point. So that means that the final displacement must be 0. It takes 9 seconds to do it. So I was sitting at 16 seconds. I added 9 seconds to that, and I got back to 0. So I hope that you can see that I don't go back to 9 over there. I hope that you've understood these graphs. I think it's looking like time for a little bit of a break. That's
I think so too.
a little bit of a brain freeze going on there at home. I'm sure that this is tons of info. What do you think,
I'm
Ty?
scanning the page, and yeah, it seems like everyone's following. It's just like, whew, it's a lot of work.
Okay, well, let's give them a little bit of a break.
Okay, no problem. So on that note, mindsetters, as you heard from Mr. Phil himself, make sure that you guys do not disappear. We're only taking a short break, so we'll be back real soon. But for now, we'll see you after this break. And welcome back, Mindsetters. Hope you had a nice little break. You went to do whatever you had to do. You went to go get water. You went to go get juice. Whatever you had to do, now you need to be paying attention with your pens and pads out and ready to make notes because we're about to continue. And remember, I need you guys to keep posting so you can win these awesome prizes, this Casio calculator and this awesome labeler. But on that note, this is where I hand over to Phil. Phil, take it away.
Thank you so much, Ty. Okay, so as Ty says, guys, get posting on the page, get helping with each other. Now, this is where it gets a little bit more complex, but I'm going to be holding your hand. I'm going to be helping you out with these graphs. Now, what I'm going to do is I'm going to show you another graph which looks very similar to the first. Now, we've done that on purpose. Is because the shape looks the same. Everyone says, oh, okay, it must be the same motion. Okay, it's absolutely not. So what we're going to do is we're going to take apart an example and I'm going to try to help you understand why this graph is different to the graph that we did earlier on in the show. Okay, so let's start reading through this, highlighting the important information. I want you guys copying this down. I need you processing this, writing this down, graphing it out with us, because unless you see it there in front of you, in the flesh and blood, it's never going to make a lot of sense. Okay, so guys, just watching science is not going to work. Okay, so what we're going to do now is we're going to take a look at a slightly different example. We're taking a look at a car which is accelerating from rest. Okay, so what I'm going to start doing is I'm going to start highlighting important keywords that you should always look out for when we describe motion. Okay, so the first thing which we are told is we are now describing acceleration. Now that's something we haven't got to yet. So it accelerates. Okay, now we're going to deal with the acceleration definition in a moment. Now it says from rest. Okay, so from rest is a big alarm bell inside my head. From rest. Oh, that's a big red light going off inside my head, and I'll tell you why. From rest means that we are stationary. Now, previously we were dealing with displacement and how it dealt with velocity. Now we're dealing with velocity and how it deals with acceleration. We're going to summarize this all for you a little bit later on in the show, so don't panic too much. So a car accelerates from rest at 4 meters per second. Now, there's something different about this 4 meters per second. It's per second per second. Now, there it is, 4 meters per second squared. Now, I can tell you now that most grade 10s don't know why it's per second per second? Well, I'm dealing with velocities. From rest tells me that velocity equals 0 meters per second. So that's my initial velocity. That's where I begin. That's from rest. At 4 meters per second. Well, now 4 meters per second, that means that every second that goes by, that velocity increases by 4 meters per second every second. Now that might seem like a lot of stuff to take in and everyone's brain is hurting, but let's start talking about velocity as just meters per second. That is my way of describing velocity. So it's 0 meters per second. After 1 second it'll be 4 meters per second. After another second it'll be 8 meters per second. So what we're doing is we're following a velocity from 0 meters per second to 4 meters per second to 8 meters per second. It's going up by 4 each time. So let's take a look and see what that looks like if we graph out the velocity. Now this is a velocity time graph. It's slightly different from the last one because now we're describing a y-axis which is very different, and that is velocity in meters per second. Okay, now you're going to see where that unit for acceleration comes from and how we can get acceleration off a graph which looks like this. Okay, now it does this for 6 seconds, and that sounds quite familiar because our last experiment was for 6 seconds as well. But we weren't describing the velocity, we were describing the displacement. How do we know what we're describing? Well, if I know that velocity is 0 meters per second, over there, 0 meters per second is a description of the velocity. So it says the velocity is increasing from 0 meters per second to 4 meters per second to 8 meters per second every second. That's where the per second comes in. Now, if that's not making a lot of sense to you, that's perfectly okay. Just keep watching. Try and stay with us. Okay, so now what I'm going to ask you to do is actually follow through this graph with us. I actually want you guys to draw this as well. I want you to copy, and I actually want you to trace your way through this. Okay, now just as we did before, what we're going to do is we're going to go 1 second forward, and we're going to try and see how much we must go up. Well, what we've got here after 1 second is that we must go up 4 meters per second. So if I trace that out, I get 4 meters per second. There we go. It falls on my line beautifully. So let's do it again. After 2 seconds, I should have around about 8. And there we go. After 2 seconds, I've got 8 meters per second. After 3 seconds, I should have 12. And let's plot that out. So you can see that I'm actually making a nice straight line. Okay, so now what I've ascertained, or what I've figured out, is that these triangles are also the same. Does this mean that we're looking at the same graph? Absolutely not. What I'm showing is that every second that goes by, the velocity increases. The previous one was a displacement time graph. That's why I say that every time you describe what's happening on a graph, start your sentence with the y-axis. The velocity does this. So let's figure out what the velocity is doing. The velocity is increasing. Okay, now let's describe how it's increasing. Well, each second that it goes by, it seems to be going up the same amount. So 1 second forward, 4 meters per second up. 1 second forward, 4 meters per second up. So you can see that it's going up by the same amount each time. That means that I have a constant acceleration. Now, what does this word acceleration actually mean? So what I'm going to do is, on this graph, we're actually going to describe what the meaning of acceleration is. And it's going to sound kind of familiar because it's a similar thing. Okay, so acceleration, how would I describe acceleration? Acceleration is equal to, and this might seem very familiar, is equal to the rate of change. And you need to know this. So rate of change of velocity. There we go. It's the rate of change of velocity. Wait a minute, rate of change, I've heard that before. Rate of change is the gradient. Well, if I start to take a look at this particular graph, I know that my y-axis is v, I know that my x-axis is t, so let's make a formula to calculate acceleration. Acceleration is equal to the change in v over the change in t. Now, if you're not that comfortable with the triangles, that means v2 minus v1, t2 minus t1. That's all that it means. It means the change of velocity over the change of time gives me the acceleration. So let's just move that out of the way. Let's make sure that you can actually see that formula. There we go. There's your definition. There's your formula. Acceleration is equal to the change in velocity over the change in time. Okay, so let's try and figure out what this acceleration is and how it relates to my graph. Well, let's do exactly the same thing we did for our first graph. I knew that from rest, we started off at 0. So what I'm actually going to do is I'm actually going to move down a little bit and swap colors. So let's start working in a little bit of purple, and let's try and see where we got all our information from. We started at 0 meters per second. All right, so that means that initially we were stationary from rest. Well, each second that goes by, I increase my velocity by 4 meters per second for 6 seconds. So that means at the end of all of this, I've got to have 24. So that means that I've got 24 meters per second of velocity. Okay, it goes on to say something else. It says, and then maintains velocity for 10 seconds. All right, well, it says then maintains. That means keep the same or conserve the same velocity for 10 seconds. So that means that I'm still going forward at the same rate. Now, this is quite different from the last graph, because when I saw the last graph, flat meant no change in displacement. That's why it's important to figure out which graph I'm looking for. Well, I've got a velocity time graph. So let's start our sentences off with, as time goes by, the velocity. So the velocity is staying the same. That means that the velocity is 24 meters per second all the time for another 10 seconds. So it's quite important to note that you are still moving for this last 10 seconds. Please, this is not a stationary vehicle. This is a vehicle moving at 24 meters per second. That's just a little bit less than 90 kilometers per hour. So 24 meters per second means that I'm still moving forward every second by 24 meters. Now, this is not a displacement time graph. We could go draw one, but what I'm going to try to do is I'm going to try and link up these two graphs with ways of measuring motion. And hopefully we actually get a little bit of a chance after the next ad break to actually show you a really cool experiment. Okay, so now how do I use displacement and velocity to calculate my acceleration? Well, it goes in that particular order. So what I'm going to do is I'm going to show you how things work in terms of measuring motion. Okay, now this might be quite a useful summary for all of your graphs and ways to actually calculate what's going on. So what I can do is I can draw a displacement versus time graph. So that's the first type of graph that I can measure. I can measure the displacement, I can measure time. It's usually the first thing that you measure. And that is the only way that you can calculate velocity. All right, let me emphasize that. Displacement versus time, the only way that I can calculate velocity is from these two first. These are the base measurements. How far and how long did it take? This is the first measurement you will always do on motion. I'm actually going to give myself a little bit more space, so let's make sure that we've got space to work around this. So displacement versus time is my first graph I'm going to draw. After that, I can start to calculate different velocities, depending on if they're the same. They might stay the same through time, or they might change. Okay, so the next thing which I'm going to plot is a velocity versus time. Let's make sure that we've got all our ducks in a row. There we go. So velocity versus time. So that's the next thing which I'm going to do. Now, let me just give you a little bit of a hint how I get from displacement to velocities. If you want to get from a displacement to a velocity, what I'm going to say is my displacement divided by my time. So I'm going to take change in x over change in time. So this is the order in which I go. I measure my displacement, I measure my time, I divide them, and I can get a velocity. If I do this multiple times, I can get multiple velocities. Well, what can I do with those velocities? Well, if you draw a graph of v versus t, what I can then do is start to move to A versus t, I can actually map out my acceleration. So the way that I do this is exactly the same way, which is velocity, or rather the change in velocity. So let's make sure that we do that. So the change in velocity as we go, the change in time. Now, if I go from x to v to a, what I'm actually doing each case is I'm calculating the gradient. Okay, so that's pretty nifty. It's a very good way of figuring out where do I start. Do I start with the acceleration, the velocity? I've got to start with displacement. So I figure out the gradient of my x versus t to get to my v versus t. I figure out the gradient of my v versus t to get to my a versus t. But we haven't drawn that yet. So what we're going to do is we're going to try to figure out what does an a versus t graph actually look like. Well, it's actually the simplest of the lot. So what I'm going to show you now is what an acceleration versus time graph looks like. An acceleration versus time graph is actually the simplest. They are always flat lines while you're in school, okay? For this very simple reason, is that acceleration versus time either means that I'm increasing velocity in the direction of motion, which means that I've got positive acceleration. That means that I'm speeding up. So what I'm going to do is I'm just going to make a note on what acceleration is. So this means that I'm increasing velocity, going faster. So increasing velocity. Okay, now what happens when I want to stop? In other words, I want to slow down. Sometimes we call that deceleration, and that is negative acceleration. In other words, I am decreasing my velocity. So that's when you want to slow down. Okay, now you've got to figure out from your VT whether or not you have a positive slope or a negative slope or no slope at all. No acceleration doesn't necessarily mean that you are stationary. That just means that my velocity is not going to change. Acceleration is all about a change in velocity. So no acceleration means that there is constant velocity. So that tells me the way in which I'm moving. You need to make sure that you know the difference between displacement, velocity, and acceleration. It's probably the biggest mix-up that you're going to find in kinematics. That is the section which deals with motion. Okay, so positive acceleration means that I'm going faster. No acceleration just means that I'm staying at whatever velocity I've already got. If I'm stationary, I'll stay stationary. If I'm moving, I'll stay moving. What about decreasing velocity over here? There we go. That is my deceleration. Okay, so my decreasing velocity is my deceleration or negative acceleration. Now, either I have positive or negative or none. You can see that this graph doesn't have any slopes, and it's probably the simplest of the lot. Now, the question is, these are all just graphs. They have very little to do with actual real-life stuff. So what I'm going to do is we're going to start to try and measure motion. Okay, so displacement versus time, velocity versus time, acceleration versus time. How do I actually go in these orders? I mean, if I start off with a graph like this, and I want to do the sequence of events, if I want to go from x versus t, v versus t, a versus t, how do I actually measure these? Well, it all starts over here. What I can actually start to do is to measure the displacement and then measure the time. So what we've actually got to do is we can measure these two. It's quite easy to measure how far and how long, because very easy to measure both of those things. I can get a ruler, I can get a timer, that's no problem. We can do that. It's very difficult to measure these because these can only be calculated from that. So we can measure displacement and time. So that's the important thing that I want to emphasize to you, is that I can measure displacement to time. It's very difficult to measure velocity and acceleration versus time directly. They're usually calculated from other values. Now, the next time you get inside a car, you can actually see that velocity versus time is actually a calculation inside that car. That car is calculating its velocity versus time. So in other words, its current velocity. It's measuring that by taking a measure of how far I've gone and how long I've taken. There's a little computer or a little mechanical device inside there which is converting the displacement of the car, in other words, how many revolutions of the tires and how long it's taking. The more revolutions of the tires in the same time means more velocity. Now, if I measure multiple velocities, I can calculate acceleration. Now, that's something that most cars don't usually measure. Now, you can go and measure that in other ways, and in grade 11, we'll show you how to measure acceleration using force, but let's keep it simple. Let's just measure the displacement, let's measure the time, and let's see how this goes. Okay, so how do I go about measuring these things? Well, what I'm going to be doing is during an ad break is I'm actually going to be rigging up a piece of equipment called a ticker timer. So a ticker timer basically gives me a way of measuring how far I've gone and how quickly I've done it. So what happens is I've got a tape which basically runs through my ticker timer. This ticker timer over here actually draws dots at regular intervals. That means that every certain amount of time it's going to make a dot. Now the tape is going to move through the ticker timer. And as it moves, these dots are going to be drawn along the tape. So what I'm going to show you after the break is how we can actually use this to measure the velocity. So just to have a diagram of what a ticker timer actually is, a ticker timer has got the tape which is being pulled through it. So there's the arrow for the tape being pulled through, and I'm going to show you how that works. Now there's a coil which tells me that it's going to tap on this sheet of carbon paper. So carbon paper is really good at drawing on things. So carbon paper is going to make dots on the ticker tape. Now when it gets pulled through, it's going to make a line of dots exactly like those that you see on the screen. And we're actually going to use that to figure out how fast something is traveling. But I think it's time to take a short little break. What do you think, Ty?
I think so too, so you can nicely prep up that experiment of yours.
Fantastic.
All right, so mindsetters, as you've heard from Phil, there's an awesome experiment coming up after this ad break, so do not go anywhere. Make sure you keep posting on the page. I'm loving the interaction on the page so far, so guys, keep on posting. But for now, we'll see you after this break. And welcome back, mindsetters. Hope you had a nice little break there. I'm not going to say much because I'm excited to see this next experiment. So before I even go on too long, I just want to send a quick note. You guys make sure you post on the page so you can get these awesome prizes. But on that note, I'm going to hand back to Phil. Phil, take it away.
Thanks so much, Ty. Okay, well, what we've actually got here is we've got a ticker timer, and we've got a power supply, and we've got the ticker tape. So what I'm going to be doing is I'm going to be dropping this weight, and it allows this tape to slide through my ticker timer. Now, what happens is this power supply is allowing this ticker timer to make dots on this tape over here. So what I'm going to be doing is allowing it to fall freely as it goes through here. So what happens as this drops, it's going to be drawing a series of dots on this tape. So now as it goes through, what's going to be happening is it's going to be making dots, and what we can actually do is figure out how far this thing has fallen, because it's going to fall down to the floor. So let's switch on our power supply, let's drop this experiment, and then what we're going to do is we're going to see what actually happens on that tape. So what I'm going to do is switch on my power supply. I'm not going to speak too much because it's quite loud, so let's switch it on. Let's put in the AC voltage, alternating current voltage, to get my ticker timer working. So there it is. You can hear that buzzing noise. That is my ticker timer. So what I'm now going to do is I'm going to allow this to drop. What that's going to do is cause this to accelerate down to the ground because of gravity. So let's do that. It's quite quick. And what we've got over here is actually a perfect tape. And I'm going to show that to you in some detail. Is you can actually start to see these bits and pieces. And you can actually see those dots as they go. Let's just switch that off for a second so I can explain. So you can see that as I hold this tape, you can see that the dots are getting further and further and further apart. Now, each one of these dots was recorded at exactly the same amount of time each. This ticker timer is calibrated, meaning that it's set to give one dot every 50th of a second. So each one of these dots that you see is drawn 1/50th of a second apart. Now, if I take a ruler, I can actually measure how far this tape went in that 1/50th of a second. Well, if I've got my displacement and I know that my time from each dot to the next dot is 1/50th of a second, that actually allows me to work out the displacement during one of these dot intervals. Now, I call the spaces between each one of these dots intervals. So from one dot to the next, I can measure the time and I can measure the displacement. That allows me to calculate the velocity. If I can calculate several velocities, that can get me acceleration. So let me just repeat that again. The idea behind a ticker tape is to get displacement, so that I measure with a ruler, and time, because this ticker timer is set at 50 dots per second. That means 1/50th of a second for each dot. What we're going to do now is try and understand how I can get acceleration from something like this. I can actually find out how fast this accelerated towards the ground because of gravity. Now that's not too difficult to do if I know how. Now ticker timer calculations really don't have to be hard. All I've got to do is remember the order of operations and why I'm doing them. So what I'm going to do now is I'm going to walk back to the board and we're going to try and explain what the meaning of all these crazy dots are. So let's do exactly that. So what I've got on the board here is just a diagram. Once again, I showed this to you just before we went away, is that I've got my carbon paper which drew my line of dots. So let's take a look at what these dots actually mean. Well, the interval, remember that the time interval over here. Let's try to figure out what it means from dot to dot. Now, if my tape is moving in the direction shown, in other words, it's moving towards the left. So I've got these dots, these red dots. What this means is that I've got the same displacement for each one of these. Now, I've got 1/50th of a second, which is 0.02 seconds between each one of these. That allows me to calculate the velocity. Now, it's quite important to note that these dots are evenly spaced. That means that they're not getting wider apart. Now, what that means is that I've got constant velocity. So there it is. Constant velocity means the same distance moved each time interval. So given the same amount of time, the same displacement. So this is very much like that boy that was walking. The same displacement, the same time. So if the dots are equally spaced, that means that I've got constant velocity. Now, positive acceleration. The distance between these dots is increasing. Now, I've just got to remember that my tape is being dragged over there. Now, if I've got my first displacement over there, let's put it on there, I can see that it's a relatively small displacement. However, if I take a look further down the tape, I can see that this displacement is much, much larger, but it took the same amount of time. That means that my velocity was increasing. So positive acceleration means that velocity is increasing. So that means that my spacing will get larger and larger and larger. That means that this object was traveling faster. And if you were paying really close attention to what was going on earlier, is those dots were getting further and further and further and further apart. That meant that that object was accelerating, and that's because of gravity. What happens when something slows down? Well, this one's actually quite easy. I can see that the initial displacement for that time period of 1/50th of a second is quite large. So it's going very fast initially. Lots of displacement in some time. What happens at the end is very little displacement in that same time. So that means that I'm covering less distance for the same time. What does that mean? That means that my velocity is decreasing. So my velocity is decreasing. All right, so my velocity is decreasing, and that is what negative acceleration is. Unfortunately, that's a little bit unneat. But what I'm going to do is, before I go, is we're running a little bit short on time, so I think I should give them a little bit of a challenge for that calculator. What do you think, Ty?
I think so. Maybe just a nice little short one. Probably.
Absolutely. Okay, well, let's put it up on the board and let's see how you guys actually cope. What we're going to do is we're going to try and figure out what my velocity and acceleration is. Now, I've got a ticker timer with a frequency of 50 hertz. Let's just highlight the important info. Right, there it is. 50 hertz is used as a trolley, runs down a track, so that means that I was dragging that paper, that ticker tape. The following sections of tape is obtained. A, B, C, D, those are the dots, okay? Show successive dots, that means one after the other. My tape was moving in the left-hand direction, okay? Calculate the acceleration of the trolley. Well, that's the end of this process. So what I'm going to do is I'm going to push you in the right direction. And what I'm actually going to do is over the next hour, I'm actually going to monitor the page, and I want you guys to start posting your ideas on what the acceleration of the trolley is. Let me give you some hints. We've got a minute or so. So what I'm going to do is I'm going to give you the order of operations. Okay, so the first thing which I need to do is I need to measure my displacement and my time. So I need displacement and I need time for one of these intervals. So let's say we do for A and B. I've got displacement, I've got my time, which is 1/50th of a second. From that, I can actually find my first velocity. So my first velocity. Now, what I'm going to do is I'm going to do it again. The reason that I'm going to do it again is because I'm going to say displacement 2 and time. Why am I using the same time? Well, it's the same time interval. And what that can get me is a second velocity. Now, it's quite important to note that I need more than one velocity. Now, what I'm going to do now is give you a little bit of a hint. I can use those two velocities to find out my acceleration, because I need a change in velocity to find my acceleration. So here's the way that you do it. First, my displacement and time to get me my two velocities. Only after that can I get my acceleration. Well, another little clue for you guys on the page is that my displacement is actually in the wrong units. So now, this is very often the way that you would measure out your displacement is in millimeters. So what I've got to do before I do anything with these displacements is that I've got to convert them into meters. So from A to B, I know that there's 5 millimeters. Don't forget to change that into meters. Same thing for B to C. Each one of these is one time interval. Okay, so go displacement and time to get my velocity 1, displacement 2, and time to get my velocity 2, and use those together to get me my acceleration. I'm going to be checking out the page to see who gets the first right answer, and I'm going to be telling Ty a little bit of something in his ear, and he's going to tell us who's going to win that calculator. But from me, that's over and out for the grade 10s for this week.
All right. So on that note, Mindsetters, as Phil said, he's going to be watching the page with me. So make sure that you guys get your posts in. And I just want to say a quick shout out to Liberty. Thank you for sponsoring the show. And this is where I, Ty, then sign out and say, thanks for having you and see you next time.